I'll begin with a word of prayer. Heavenly Father, we thank you again for this day. Students, this class, just pray that you be with us, help us to glorify you in what we do, and just for the students to ask good questions as they have them. Lord, in your name I pray, Lord Jesus. Amen. So I figured while I had the top hat out, I'd just show you guys how this silly website works. It's kind of fun.
Can you put the code back up real quick?
It doesn't matter, but sure. 3402. That does raise an important question, though, which is, am I actually going to take attendance? And the actual taking of attendance is happening now. Here you go. Sorry, it's gotten a little bit scrunchelled. I'll have to go iron this later. So this is math3d.org, which I think is pretty good. Like, I was originally a little bit annoyed because it seems like they're implicit. Okay, so like I have spent about a half hour Googling 3D graphing apps. Well, not apps so much, more websites, because I don't like apps. Because apps are on your phone, and there is no good way to punch in the sine of x squared plus y squared divided by z equals to the inverse hyperbolic tangent of x, y, z in any kind of reasonable speed with thumbs and pull up menus. You want a keyboard, right? Keyboards for real work. So anyway, this is this is the best I've found at the moment. There used to be better ones, but they all, like most of them, they don't do well with doing something like plotting x squared plus y squared plus z squared equals to a constant. Like, so if you set a function of x, y, z equal to a constant, this is so-called level surface. All of these free apps, they're kind of choking on these. They're not doing a very good job on them. This one kind of did it. I showed you. I clipped a screenshot of the problem in your homework, right? Which was that's actually a really interesting equation for a torus, right? It's a donut. That weird equation. But this is useful because at least we can plot curves. So like, I'll show you. I'll try to show you. I've had this window open for a few days. Sometimes they lock up, you know. Well, so one thing is you can kind of move it around like that, which is kind of cool. The other thing is, all right, so let's talk about what's going on here. I've plotted a few different things. See, I plotted a vector. See this 3, 2, 1 vector? See what happens if I, like, for example, change this to, I don't know, 8. Oh, that makes it go way out there. If I change that to like -2, it goes the other way, right? So you can visualize a three-dimensional vector in x, y, z coordinates if you want. Like, this is a tool you could use if you're, kind of frustrated with my kind of pictures. You could open this up and just stick them in there and see what they look like, right? Easy. It's really easy to do. Now, the other thing you can do is plot parametric curves. So like, see the red curve? The equations for that are x equals cosine t, y is equal to 2 plus q, and t. The other thing, the reason I really like this one over the other websites is this allows for the easy implementation of what are called sliders. A slider is a variable that you have control over. See, this q is a variable. I control it up here, which means I can study what happens with the red curve as I change q. What happens? Well, let's find out. See what happens? Oh man, not like that kind of. Don't do that to me. So what's doing? It's moving the curve, right? So we're moving the curve in what? In the y direction. That makes sense? If you're either adding or more or less of something. And if you want, you can even do this. Whee! You can animate what's happening. Yay! All right, super fun. Let me make this red curve go away. Actually, let me not do that. Up here, you got this cosine t squared, sine t squared t curve, right? Which you can see is this wacky curly Q here. And what have I done? See that right there? See how I did this? I put a slider into the domain. So the way this is working is the domain, the range of the parameter. It starts at -2 pi and it goes up to big T. But I'm controlling what big T is. I can change it. And as I change that, what's going to happen? You're going to see how the curve traces out. See, you're going to actually be able to see how the curve traces out. So, of course, if I get past, -2 pi is what? That's like 6.28, right? So we never quite get back to the start of it. If I made this -7, what would happen? Oh, it won't let me. Huh. Well, anyway. So here's what happens as t increases. I'm just tracing out the curve, right? Here it goes. Oh, look, that was kind of unexpected, wasn't it? Look at that. Whoa, and then it does that. See that? Anyway, so here, if you want to see it, voila. All right. Now, we could do other things with this software, right? Like, you could add objects. For example, I could add a vector field. Whoa, look at that. A vector field is an attachment of a vector at each point in space, so you can study that kind of thing. Listen, I've only started playing with this, but you can do a bunch of things with it. I think it's worth, if you want something to like play around with what things look like, this is not a bad thing to use. Of course, if you spend, I don't know, like 10 hours on Mathematica, you can get good at that too, right? So, but this took me 20 minutes to get this far. And you guys are smarter than I am with technology for sure, so, you know, there you go. All right, enough about that. I just wanted to spend like a few minutes of class talking about that because I sometimes forget to look at these things. Now, if I was smart, I would show you my example 1 here. But well, I don't know, we'll see. If there's time, I'll come back to it. But. All right, so before I get into things, are there any questions? So noisy. Okay. We used to have these ones on strings. They're like based on a spring, and they just, so much fun. Satisfaction of pulling the string. I miss it. All right, well, here's a problem. Let's suppose we have R1 of t parametrized by, I don't know, cosine t, sine t, and then 2t. All right. And also I have R2 of t equal to, now let me just think about this for a second here. 0, 1, pi, all right, plus t times, I don't know, 1, 2, 3. So what we're looking at here are two paths, all right? You probably should be able to do this. You should be able to describe one of these paths. What's the second one?
The line.
That's a line, right. What's the derivative of the line? What's dr d2 dt, by the way? This would be what we call the velocity vector of the path, right? And also, what happens when you differentiate this? Derivative of the constant vector, 0. And this, you can just write, so really you just have ddt of t times the vector 1, 2, 3. And the properties we proved last time is if you've got a constant vector and you've got a derivative of a scalar function times a constant vector, you can pull the vector outside the differentiation. So I can erase this, like so, and just put the differentiation just like that. In other words, the derivative is just 1, 2, 3. Now I did this for this example, but it's true for an arbitrary, if you have any line, right, which has like r naught plus t times v naught, the derivative is just the v naught, the direction vector, as we've, in our usual standard parameterization. Now, what would the derivative, so that's a line. I think we can all agree about that, right? Do you guys understand what this other one is? Okay, fine, I guess I can. It's a helix. I'm stupid. Let me get this thing back out again. I'll show you. So what did I have? I had cosine t, sine t, right? And then 2t, is that right? And I'll start let's start it at 0 for the sake of discussion here. Oh, the exponents are wacky. All right. And then, let's see, what's the equation for my line? It's a parameterized curve, right? How's it go? T, and then what? 1 plus 2t. And what's let me get that q out of the way here. And then what's then what, pi? And by the way, I just hit pi, it automatically changed it to that. That's nice, right? Good coding. And let's see here, I'm going to let that also go from 0. Well, I'm going to let that go from, say, minus 2. Oh no, well, that's not good. Thank you. Was I supposed to have? Yeah, so I'm just supposed to have t there, right? Okay, good. And I'm going to let this. I'm going to let them both go to t. So what I'm doing, undefined. Oh, I did q, didn't I? I'm going to put q up here too. Since I still have my q slider. Why is that vector still there? I thought I got rid of it. Oh, that's my helix. Thank you. Let's see here if I can I zoom in? Well, anyway, let me stop. So let me just,
You might be able to zoom in axis and camera.
axis and camera, you think a zoom?
I have no idea.
That seems like a reasonable,
If you scroll.
if I just scroll. Oh, there we go. Yeah, I just pinched it, right? So like the usual, it's actually got the usual camera, you know, like you guys zoom in on your pictures in the camera. It's like that. All right, now let's watch what happens as Q goes on. All right, so what's going on here? Well, it's not cool. They should. I think the coding is, if we look at, oh, right there. Oh, okay, I know what's going on. So you can see that they do intersect at a point, right? That's not, if I zoom around, here, let me just look at this much, right? So if we zoom around, you can see it's not just a trick of the eye. Those curves actually do intersect at that point. See that? Is it a collision? Is that a collision? Well, it's not a collision, right? Because the red one goes there before the blue one, right? So they're crossing the same point in space at different times. So you guys told me this is a helix, that's right. What's the derivative here? All right, great. Where is this point of intersection? How do you find points of intersection? Well, generally speaking, what you do is you set like R1 of t equals to R2 of s, and then you look for solving, you know, cosine of t equal to s. You've got like sine of t is equal to 1 plus 2s. You have to solve 2t equals to pi plus 3s. See R2 of s? Well, that could be annoying. R2 of s, I just put the s in the place of t, okay? Oh yeah, if you don't mind, thank you. So to look for a point of intersection, we have to solve, because we don't know that the paths are intersecting at the same parameter, right? So I will soon regret my life if I don't pan over here. All right. So, all right. So to find the point of intersection, we have to solve these for, the question is there a choice of t and s which makes these equal? We've seen from the plot that, yeah, there is. And also from the plot, if you mess around a bit, you can see it's happening. I mean, I know this because I just made the example, right? But around 1.5, between 1.5 and 1.6 is where it's happening, right? For t. So what do you, well, you see we can solve this, right? This gives us what? Well, can we solve it? Let me say it this way. We can replace, man, that's annoying. I'm easily distracted, as you well know by now. But here t is equal to pi over 2 plus 3/2 s, right? So if I plug that in, I've got like cosine of pi over 2 plus 3/2 s equals to s. So one obvious solution to this, right, is what?
S equals 0.
Yep, s equals to 0 solves that. Because we know cosine of pi over 2 is 0. If you take the inverse cosine of both sides of that, you'll get pi over 2 plus 3/2 s equals to pi over 2, which then solves to give cosine of 0. I mean, it gives s equal to 0. So that has s equal to 0. If that's s equal to 0, what's t equal to?
Pi over 2.
Yeah, t equals to pi over 2 because you plug that, plug this back into that equation, it gives us that, right? So indeed, what's going on here is that R1 of pi over 2 is equal to R2 of what? Of 0, right? And these points are both, which point is it? It's the point 0, 1, pi, which is how I made up this example, right? What I did was I picked a point on my first curve and I just made a line, had that as its base point. If I did that, I knew they were going to intersect. That's how I made this example up, okay? Now let me ask a question. So now that we know these two curves intersect, you guys agree? So like, my picture, roughly speaking, is you got a helix. It's one of these deals. That's my picture for the helix. And you've got a line, which was like, here-ish, let's say for the sake of artistry, right, like that. Then you can ask the question, that point is 0, 1, pi. We can ask the question, what's the angle between the curves at the point of intersection? How would we define angle between curves at a point of intersection? What would we, yeah? Yeah, the angle between their tangent lines, right? In other words, the angle between the direction vector to their tangent lines. In other words, the angle between their velocity vectors, right? So these guys up here, these are actually the velocity vector fields. As you notice that those are both actually technically functions of t. So as t progresses, that's the velocity at time t. What are we interested in? If we want to find the angle between these curves, we need to look at the velocity vectors here, right? We need to compare this vector against that vector, right? So we need to compare the red one was R2. So we need to look at R2 prime of 0, that's my s, right? Versus R1 prime of t, which was, well, pi over 2. Now you can't go wrong with R2 because it's got a stupid constant velocity vector field, right? So you can't, I don't think you can get that wrong, right? But you got to be careful to get the right parameter to put in to get the appropriate velocity vector for the helix, right? Which is pi over 2. So what do we get? So R2 of 0 is just 1, 2, 3. R1 prime of pi over 2 is, well, you got to go up here, right? Plug pi over 2 into that, what'd you get? Minus 1, 0, 2, right? What's the angle then between these? What's the theta here? How would you find that? Well, we're back to week 1, right? So we calculate the dot product. and use the cosine formula, right? So like, what's the dot product of these two things? So we got -1, 0, 2, dot product with 1, 2, 3, equals, what's the length of the first one? Well, square root of 5. What's the length of the second one? What's 1 plus 4 plus 9? Square root of 14, right? And then cosine of the angle we're looking for. So what's that angle? Let me put this thing away so we're not feeling kind of cramped. So the angle I'm looking for here, the angle between the curves at the point of intersection, should be cosine inverse of, what's this dot product work out to? I got a -1 plus 0 plus 6. That's 5, thank you. So we've got 5 over root 5 times root 14. If you like, you could just make a root of 70 down there, right? Product of the square roots is the square root of the product. But anyway, it's that. What's that give us? This I don't have memorized. I mean, I could derive it if you paid me money. If I was on a desert island and I had some time, like, we could work it out from Calculus 2, right? You can find the power series for it. But you got to do it in the, if you want degrees. Well, anyway, I shut up. What is it? My calculator says 53.3 degrees. So there you go. That's the angle of intersection between these curves. So this is one of the obvious applications of like differentiation, right? If you have a path, we can differentiate it, and that gives us the velocity vector field, which tells us the direction that the curve is going at any point, right? So then we can answer interesting questions like this, like what's the angle of intersection between two curves, right? Now this back here, this isn't really calculus, right? This is just annoying pre-calculus kind of stuff. Do two curves intersect? Do these curves collide? Well, the answer is no. They don't intersect at the same parameter, right? If we think of S and T both being time, they don't intersect at the same time. How could I make them intersect at the same time? How could I make this line collide with that path?
You shift it backwards.
Yeah, right. So I just take this t, and if I replace that with like t minus pi over 2, it would have collided. That would have made the colliding tangent. That wouldn't have been a tangent line, but it would have been a colliding line with the path. All right, and the angle would have been the same, but then it would have collided. So you can try that out for yourself on the website later if you want. All right, so any questions before I go on? I just wanted to do a kind of, you know, I don't know what kind of example you call that. Maybe a meaty example. Listen, so it's important that you read chapter 2. Like, read my examples on the calculus of curves. I have, in that, made an attempt to go over pretty much every nook and cranny of calculus 2 you've probably forgotten in terms of like differentiation of inverse functions and fundamental theorem of calculus part 1. Do you guys know what that is? Let me build it into my example 2. Suppose we have r of t equal to, oh, I don't know, the integral from 1 to t of the hyperbolic sinh cubed of the square root of t plus 7 divided by t cubed minus cosine inverse of t. There, that's pretty horrible. Comma, inverse tangent of t, comma, inverse sine of t. All right, there's a pretty horrible path. I wouldn't advise graphing this. This is just for the purpose of reviewing your calculus 2, which you may be a little rusty on. There's one other thing I need to do to this to make it worse. Let's just slap a t squared right here. There. Now it's really horrible. All right? So how do we, if we differentiate this, right, dr dt, how's that go? Well, we have d dt, remember, like this. Oh, my bad. Oh, goodness gracious, guys. first of all, take away my license to teach Calculus 2. This is no good. I can't have an integral with no measure. That's not good. And also, I'm using the same variable here as here. That's also not allowed. Let me fix it by changing these t's to taus. Now, the other math professors will not fire me. I mean, they don't have the power to do that, but they won't advocate for my firing, let's say that. There we go. Now, it's all good. So, see, I have to have a different variable of integration than I have. If I have a bound, I can't have the same letter there. That's meaningless. I have to have a different letter. Okay, so we got that. Then what? Well, then we've got d dt of t squared inverse tangent of t, right? Comma d dt of inverse sine of t. So this was essentially our definition of the derivative of a path. We differentiate each component separately, right? Okay, so then what? How does this first thing go? How do you differentiate something like that? Do you guys remember?
Evaluating the limits.
Right. This is fundamental theorem of calculus 1. Says you just plug in the bound. That's it. It's kind of stupid, but so we just change the taus to t's, and that's it. Right? I mean, you see this at the start of calculus 1, and we talk about it on calculus 2 maybe a couple times, but then it kind of gets left out of the discussion. But it is nevertheless something we know and we should remember. Now, it's important that the bound is matching. If the bound is not matching, then we have to multiply by the derivative of the bound, which is by the chain rule. Yeah.
Would that still work since you have tau there now?
What do you mean?
Well, you have like d tau there,
Yeah.
and then you have ddt there.
Like the usual letters we used before would be something like ddx, right? Of like integral from 1 to x, 1 to x of, say, sine of t squared dt. Like that's the notation we tended to use before in like Calc 1. And then the answer was sine of x squared, right? So here, my the role of t is being played by tau here. I'm differentiating with respect to t, like I would have been differentiating with respect to x back in Calculus 1. I don't know if that answers your question or not, but it's like you may be confusing the meaning of t in your mind because you've got like this idea preloaded from Calc 1 if your memory's really good. No? Okay, well. The tau has to go away. The tau is a dummy variable of integration. T is the thing we're differentiating with respect to. Like we're calculating this derivative at time t, so the answer should be in terms of t. Did I write a tau? I don't think I did. Okay. I mean, if after all of that discussion, I had a tau sitting up there in my next line, it would be like really annoying to me. This is the kind of mistake I usually make when I'm talking to a student about whatever I'm correcting, that's typically a mistake I'm just making on the board. That's my luck. Wait a minute, I don't believe in luck, so anyway. How about the next one? That's a what? That is a product. So we must do the product rule, right? So this is 2t times the inverse tangent of t plus t squared times the derivative of inverse tangent. What is the derivative of inverse tangent? Do you guys remember? 1 over 1 plus t squared is correct. So if you've forgotten that, well, you need to review your basic derivatives, right? And then what's the derivative of inverse sine? My bad. Derivative of inverse sine is, I think, so, all right, so here's two choices. Is it 1 minus t squared, or is it t squared minus 1? What do you guys think? And why? 1 minus t squared. The reason that has to be is the domain of the inverse sine is the range of the sine. What's the range of sine?
0 to 1.
Minus 1 to 1, right? Minus 1 to 1. Sine goes from minus 1 to 1. So whatever I'm feeding into the square root, right? It has to be in that range, -1 to 1. I better be feeding something positive into the square root. I'm dividing by it, right? So this guy, 1 minus t squared, is positive for -1 to 1. It has to be that. If you think about the domain and range issues here, it has to be 1 minus t squared. Now, of course, you could derive it, right? Do you guys know what the derivative of inverse hyperbolic sine is? Better question to ask is, do you know how to find the derivative of an inverse function if you forget about it? Yes, no? Implicit differentiation is the answer, right? Do you guys want me to show you? Have you forgotten? Yeah? Okay. So just, this is really Calc 2, but I'll just take a second since we have time in here. If I set y equals to inverse hyperbolic sine, I want to find the derivative of this guy. So I start by just writing y equals the thing I'm trying to find the derivative of I've forgotten. All right? Next step, I take the function of both sides, in this case sinh. So this gives me sinh of y is equal to x. All right? This implicitly defines y as a function of x, so I can do implicit differentiation. I implicitly differentiate this. This gives me cosh of y dy dx equals to 1. All right? Well, dy dx is what I'm after. So let's solve for it. So dy dx is 1 over cosh y. But remember, the fundamental identity for cosh and sinh is what? Cosh squared y minus sinh squared y equals to 1. So you see, cosh squared y is equal to 1 plus sinh squared y. And because cosh is greater than or equal to 1, if I take the square root of this equation, it unambiguously gives me that hyperbolic cosine of y is equal to the square root of 1 plus the hyperbolic sine squared of y. Right? But what is hyperbolic sine of y here? Hyperbolic sine of y is x. So you see this is actually 1 over the square root of 1 plus x squared. And there you go. The derivative with respect to x of inverse hyperbolic sine of x is equal to 1 over the square root of 1 plus x squared. So this is how I derive these things if I forget them in a pinch. And you can do a similar derivation to derive the 1 over square root of 1 minus t squared we just pulled out of our hat. Right? Is this calculus 3? Definitely not, right? This is calculus 2 stuff, but it is prereq, and I will ask you to differentiate things we differentiated before. And I don't try usually to trip you up, but if you've forgotten things. Listen, in a typical calculus 3 class, in my experience, if I ask a quiz like day 1 and there's like a product rule in it, 30% of the students are going to get it wrong because you're just rusty, right? And certainly homework 1 will not have helped you shake loose the cobwebs of calculus, right? Because there wasn't a lick of calculus in there, right? It's all this fancy schmancy vector stuff you didn't know before. Some of you. Anyway. All right. Any questions? All right, let's go on. So the quiz tomorrow is just going to be on like differentiation and integration of paths. Maybe finding an angle between two paths is a possibility. All right. And possibly the thing I'm about to just show you. All right, so, well, no, let's cut the quiz off right where I said. The things I'm about to do, not on the quiz. It's tomorrow after all. I want to give you guys a little bit more time to let things set in before I quiz you on something, right? So what I'm about to start is, oh, thanks. I don't see people move the camera, then I assume it's not been moved, but So what I'm about to start is probably not quite following my planner, but I just think it's helpful for us to get this all in front of us here right now, just to put it all on the table. All right, so which is physics of 3D motion. And we're not going to like go too deep into this. Like I'm not going to be talking about, for example, Newton's second law or anything like that. We're just talking about the formulas as follows. Just this, okay? If we think about r of t being the position of an object, well, that's the position at time t. All right, position at time t is that. If we differentiate it, that gives us the velocity at time t. All right. Then what? Well, what happens if you differentiate again? We get a of t, which is dv dt, right? These are all vectors. Notice these are all vectors. And we haven't used this notation before, but there is a second derivative notation for position, d squared r dt squared. So just like you have, you know, y prime prime, you can have r prime prime as well. And this is the acceleration at time t. All right. What's past acceleration? You guys know?
Jerk?
Yeah, the jerk. So I guess if you want, the jerk is equal to dA dt, which is the jerk. And that you've experienced if like you're on a train and you're going from a flat section to like a curved section. As you go from the flat to the curved, you notice the train kind of go, ah! That's the jerk being non-zero. It's essentially a discontinuity in the acceleration. All right, so yeah. Now we can, standard example 3. How about this? If you're given, you know, r of t, we'll go back with my t squared, and just to mix it up, we'll do t times 2 to the 3t. There we go. That's something we haven't done yet. That should help us shake loose some of the cobwebs in our differentiation, right? So what's the velocity here? If that's the position, what's the velocity? The velocity would be 1, differentiate t squared, 2t, right? Differentiate this. So what do we got? We had a product rule again, right? So the first term, hopefully everybody gets right? You got yourself a 2 to the 3t, because differentiating t gives us 1, right? Then we get plus t times what? What's the derivative of this thing? Well, what it gives you is the natural log of 2. The natural log of 2 times 2 to the 3t. But then what? Notice that the argument, the input to 2 to the 3t is 3t, right? So the chain rule slaps another 3 on the answer here, times 3. Now that's bothering me. Let me clean it up. So the velocity at time t is 1, 2t, 2 to the 3t we could factor out, right? And that's 1 plus 3 natural log of 2 all times t. Now you notice here you have options, right? Like, if you want to emphasize that the velocity is being calculated at time t, you can write the of t here, right? That's not multiplication by t. This is a fundamental confusion ever since functions have come on the scene, right? Is f of x f of x, or is it f times x, right? This is something we just have to deal with from context. That's also an issue here. But usually, if you write v of t of r of t, this is not multiplication by t. This is saying I'm taking this function at time t, right? And if you want your equations to be less cluttered, you could just leave off the of t, right? So, which will upset a certain class of mathematicians greatly. But anyway, whatever. They're not here. So, actually, maybe you're that mathematician just in younger form, and I'm offending you deeply. I don't know, it could be happening, whatever. But Don't tell me that. I'd have to fail you to stop your kind from progressing. Just kidding. I'm not a Democrat. I don't believe in canceling people. Sorry, is it too soon? Let's see. I should say something equally annoying about Republicans. What could I say? I don't know. So many things. Does that suffice? I think that suffices. All right. So I don't know. I'm just disinterested in the Republican primary right now, honestly, guys. Like, because while I want to get excited about this or that primary candidate, in my heart, I know Trump's already won. Like, it's pointless. He's going to steamroll over them. It doesn't matter if he's in jail. He could be in shackles in front of the Supreme Court or whatever, like people throwing tomatoes at him. He would still be the Republican candidate. He could be dead. He would still be. we'd still vote for him. I mean, that would make us more like Democrats, I guess, in some sense, if you're that. But anyway, I digress. So sorry. Oh, can we differentiate again?
Yep.
Yep. So the acceleration here is, well, 0 to 3 times the natural log of 2 to the 3t. And if you don't mind, I'm going to try to do this all in my head. And no, I'm not going to do that. Bad things will happen if I do that. I will not. That's my derivative of that times that, and then plus 2 to the 3t times the derivative of this, which is just what? 3 log 2. Sorry, it got ugly. Unpleasant, yes? But there it is. That's the acceleration of that path.
Why are the 2 plus signs?
You know, that's a good question. I'm not sure how to answer it. I just feel like the plus should go both places, but I understand maybe it shouldn't. And yet, I think as a point of understanding my work, I think I always put the plus both places. Now, maybe I should do this. Now that you brought up the question. No, wait a minute. Oh. Thank you, Sam. That is an improvement. For this joke to land, this can only land here. Like I could, if you tried to land that joke in college algebra, it would not happen. Sometimes, as a social experiment, I will tell the same joke here and in college algebra just to see, like, what happens. Yeah. Oh, they can watch this if they want to see my, you know. I would hope, I mean, I think that there's a good chance college algebra wouldn't feel insulted. They'd feel like I'm complimenting them on not being nerds, right? So, yeah. Okay, so on the flip side of things, you can integrate, right? So what if your acceleration is equal to, I don't know, minus g z hat? And you also know that your position at time 0 is equal to r sub 0, and your velocity at time 0 is equal to v sub 0, right? You can integrate this, right? So integrating gives me that, you know, the velocity is equal to minus gtz hat, right, plus v naught. That's the velocity at time t, rather. So if I integrate, I get that. Now, how do I know I get plus v naught? I mean, technically, I should add a constant, right? And then I can work out that constant vector has to be v naught. So you can check it out. V of time 0 has to give me back v0. It forces me to add this vector over here in order to match this. These right here are called what? Initial conditions, right? So in order to fix the velocity and the position, if you're given the acceleration, you need to be given an initial position and an initial velocity, all right? So, and then if I integrate again, that gets me to the position at time t. What happens when we integrate? Well, it turns out we're going to have an r naught here, all right? I'm just anticipating the answer a little bit. When I integrate v naught, I get t v naught. When I integrate minus gt, I get minus 1/2 gt squared z hat. And there you go. That is the position as a function of time if your acceleration is a constant minus gz hat. If you're taking physics, if you use z as up and down, these are actually the equations for projectile motion. Like this. That's a good marker. I need to go get that back in a minute. But all right, so any questions? Listen, there's a little bit more in terms of, like, I think I've skipped over like the chain rule. If you have a, if you have a vector, if you have like r of g of t, where g is a function of time, and you differentiate something like this, guess what happens? You get like dr dt at g of t times dg dt. This is a chain rule. So here, for example, oh goodness gracious, if I had r of, uh-oh, I'm losing it, r of sine t, and I was differentiating that, what I would get is dr dt at sine t times cosine t. This is going to be important to us. This chain rule is going to be important to us like in the next lecture, because we're going to talk about arc length, all right? And we're going to need to talk at least a little bit about reparametrizing a curve. All right, you guys, what's reparametrizing a curve? It means taking the formulas you have, taking the parameter that you have, and like replacing it with a new parameter that's related to the old parameter in some kind of nice way. It turns out when you do that, all you end up doing multiplying the velocity vector is by the derivative of the reparametrization function. All right, so we'll look at that kind of thing tomorrow, and that's part of the start of a discussion, which is kind of a deeper, more geometric discussion, which is, if you have two curves in space, right? When are they the same? Like if I give one of you guys a slinky, right? And if I give another of you a slinky, and you have them stretched in the same way, right? And one of you is holding the slinky like this, and the other one of you is holding the slinky like this, let's say, you should see that, everything else being the same, those are the same curve, right? But one of you would be here, one of you would be there. Those curves would be what we would say, they'd be congruent curves in the sense of high school geometry, right? A congruent curve, same shape, same size, right? It's just been moved in space by some kind of rigid motion, right? You've moved it, you've rotated it. So a question that we'd like to ask going forward is, can we develop rules of calculus to decide when two curves in three-dimensional space are actually the same curve, high school congruent geometric congruent? To do that, we're going to have to look at arc length, and then we're going to look at the tangent, the normal, and the binormal fields, which will describe actually the geometry of curves. To do that, it's all just differentiation and vector algebra, though. So that's where we're going. I'm technically a little bit off my schedule, but we'll be okay.